Alrighty, and then the last talk of the consensus session is post-quantum single secret leader election, SSLE, from publicly re-randomizable commitments. And today we have speaking with us Aditi Partap from Stanford University. So let's give it up for Aditi. Hopefully it's working here.
Hi everyone. Hopefully I'm audible. Okay. Alright, okay. Hi everyone, I'm Aditi. Thanks for the introduction. And today I'll be talking about our work on post-quantum single secret leader election or SSLE from the randomizable commitments. This is joint work with Boneh and Lior Rotem at Stanford University. So let's start with looking at leader election protocols. We've already seen this in a few talks this morning. At a very high level, as the name also suggests, these protocols allow a set of parties to come together and jointly select one leader out of them. These play a fundamental role in distributed computing and consensus protocols. Specifically, they are instrumental in blockchains as well. At a very high level, we can think of the leader as the person who publishes the next block in the blockchain. Now, let's see what properties we might want from a leader election protocol for it to be securely used in our applications. The first property is fairness. At a high level, this means that all the parties should have an equal chance of being elected as the leader. You can generalize this in proof of work and proof of stake, but for simplicity, we'll consider this assumption. The second property that we want is uniqueness. This means that only one party should be selected as the leader. Now, the next question is if there exist leader election protocols which satisfy both these properties. It turns out that the proof of work consensus mechanism implicitly has leader election with both these properties. What happens in proof of work at a very high level is that each party has a cryptographic puzzle to solve, and the first party to solve the puzzle is the chosen leader. This party can then publish the next block along with the solution to this cryptographic puzzle, and anyone can come along and check that this solution is indeed valid, meaning that this person is indeed the chosen leader. So, leader election is baked into the proof of work mechanism, and this leader election is both unique and fair. But the problem is when we move to proof of stake, there is no such implicit leader election. So we need some sort of a separate protocol to choose the leader. Alright, so now let's try to design a leader election protocol that is fair and unique. Let's make our lives easier by assuming that we have a randomness beacon which is good and also publicly verifiable. Turns out that with such a randomness beacon, it is pretty much trivial to make a leader election protocol. What we do is we simply use the randomness beacon to choose one party out of the list of parties. And this is trivially fair and unique if we are using a good beacon. So we can use this randomness beacon based protocol in proof of stake. And the party selected by the beacon will now publish the next block. And because the beacon is publicly verifiable, anyone can check that this party was indeed the chosen leader. But there is one problem here. The beacon is publicly visible, so everyone knows who the future leader is going to be. This means that this leader is now an attack for a target for attacks. For example, an adversary could do a denial of service on the future leader, and this will harm the liveness of the blockchain. The underlying reason that's causing this issue in our protocol is that the leader's identity is visible to everyone before the block is published. This is in contrast to proof of work, where the leader's identity is revealed only once the block is published. So there's no way to attack a future leader in proof of work. There can be many ways to solve this issue, but what we do is that we require an additional property from the leader election protocol, which we call unpredictability. And at a high level, this means that the leader's identity should remain secret until they reveal themselves, for example, when they publish the block. A leader election with all these three properties is called single secret leader election or SSLE, and this was formally defined by Boneh et al. In 2020. To convince you that this is indeed an important problem, we have the Ethereum roadmap here from 2 months ago, from August, and it shows secret leader election as the solution for this liveness problem that we just saw. Alright, let's move on to constructing SSLE protocols. There has been a lot of work since 2020 in building SSLE protocols. There are many constructions which use discrete log hard groups as their basis, including the original work of Boneh et al. And also Whisk, which is the Ethereum proposal inspired by the Boneh et al. Work. Then there has been a lot of other work as well, which uses MPC to build SSLEs. There are other works which are based on threshold FHE and also on isogenies. But the dimension that we'll compare these works on today is post-quantum security. So all the discrete log-based constructions are not post-quantum secure. For MPC, it depends on what assumptions you use to instantiate the MPC. And both threshold FHE and isogenies are known to be believed to be post-quantum secure. But so far, there has not been an efficient lattice-based construction. And the reason why we might want to consider lattice-based constructions is that we have a far better understanding of lattices and their hardness assumptions as compared to isogenies. This brings us to our work, where we construct a practical lattice-based SSLE protocol. We do this in two steps. The first is that we generalize the Boneh et al. Protocol, which we also refer to as BEHT. And while doing this, we introduce a new notion that we call re-randomizable commitments. So these are some special commitment schemes that we'll see today. And the second step is that we build two lattice-based RRC constructions or re-randomizable commitments. The first one is based on NWE or the learning with errors assumption. And the second one is based on ring LWE, which is the ring version. And both these assumptions are very standard assumptions in the lattice world. Okay, so we'll start with the first part, which is generalizing the Boneh et al. Protocol. So I'll cover like a very abstract high-level view of the protocol. The main building block that this protocol uses is a special commitment scheme, and we'll cover what that means in a little bit. And at a very high level, it's a commit and shuffle type approach. Okay, so we'll go through that in a bit more detail now. Let's say we have 5 parties here. So the protocol execution can be split into 3 steps. The first one is the commitment step. Here, each party first samples a random number k and then publishes a commitment to this k using the special commitment scheme. Each party also publishes a hash of the value k that they sampled, and we'll see why we use this later. The second step is the main part of the protocol. We call it shuffle and re-randomize. Here, each party takes turns shuffling and randomizing this list of commitments. In more detail, we have the first party here which comes along, and the first thing that it does is it shuffles the list. It just means that it applies a random permutation to the list of commitments. The next thing that it does is that it re-randomizes each commitment. What that means is that if we consider this new commitment to K2, it should look like a fresh commitment to K2, meaning that it is independent of the first commitment to K2 that was there in the first step. The third thing that this party does is that it publishes a zero knowledge proof that says that I have shuffled and randomized the list correctly. Now the second party comes in and does the same thing. It shuffles the list and applies a re-randomization to every commitment. We keep going till every party has done this once. What happens here is like at the end of this step, we have a list of commitments, all of which are re-randomized. And the main thing to notice is that no coalition of parties can correlate the final commitment to its corresponding original commitment. And this is some sort of unlinkability notion that we'll see in more detail in a little bit. Moving on to the third and the last step of the protocol, it's just random selection. What we do is we use the randomness beacon to select one commitment out of this set of 5 commitments. So let's say it selects the second commitment. Now each party will try to open this commitment using its k value. So now party 3 will realize that it's the chosen leader, but no one else will know that party 3 was the chosen leader. The last thing is just the usual thing. So this party will publish a blog, and it will also publish a proof pi along with the blog. And this proof will include the value k3 and some opening to this commitment. So now anyone can use this proof pi to check that this party is indeed the chosen leader. Okay, so now we've seen a high-level overview of the Boneh et al. Protocol. The next question is if it indeed satisfies the 3 properties that we wanted. In terms of fairness, it is actually guaranteed straightforwardly by the use of the beacon and the proof of correct shuffle. But for uniqueness and unpredictability, we need to look into more detail of the commitment scheme that we use. This leads us to a notion of re-randomizable commitments or RRCs. Now let's see what properties it would need to satisfy for our SSLE to be secure. So the first thing is it should be re-randomizable. So what that means is that if I commit to a value k, then anyone else should be able to randomize that commitment without knowing my secret k. So that's the first thing. The second thing is that once anyone has randomized the commitment, I should still be able to open that commitment only with my value k without knowing what randomness you used to randomize the commitment. And this is important for the correctness of our SSLE protocol. The second property that we want is binding. This is the standard notion of binding for commitment schemes. This means that it should not be possible for an adversary to find a commitment and two distinct openings, K and K prime, which are both valid. And this is important for our SSLE protocol to choose a single leader, meaning for its uniqueness. The third property that we want, it's unlinkability. I hinted to this a little bit earlier. So at a high level, we want that the final list of commitments should be unlinkable to the original commitments. And we formalize this by saying that if we are given two commitments, and if I re-randomize one of them, then you shouldn't be able to tell if I randomize the left one or the right one. And this property is necessary for the unpredictability of our SSLE protocol. Okay, so the Boneh et al. Work, which was the first work in this space, constructed a re-randomizable commitment based on DDH. So this commitment was perfectly binding, it's also unlinkable, but the main issue is that it's not post-quantum secure. Okay, moving on to our work, we construct two lattice-based RRCs. The first one is based on LWE, and I will cover that at a high level today. Okay, so we'll start with a flawed attempt, and if we have time, we'll see how to fix it. So the random value k that each party samples is now a vector in ZQN. And to commit to this random vector, we use a standard lattice-based commitment scheme where we first sample a random tall matrix A. So this matrix A is in ZQM by N. And the commitment is a tuple of the matrix A and A times k plus mu. Here mu is a short noise vector and it's usually sampled from a Gaussian distribution centered at low norm vectors. To open this commitment, I can simply give you my vector k. And to test that this is indeed a valid opening, what you can do is you can check if A times k is close to the vector B, which is the second part of the commitment. And notice that this is indeed true for an honest commitment because we sampled mu from a Gaussian with, so mu is going to be short. Okay, now the next thing is if this commitment scheme is re-randomizable. What we can do is we can just sample a random Bernoulli matrix R. So this R is going to be uniform in -1, 1, m by m, so it's a square matrix. And then we simply multiply both coordinates of a commitment scheme by this matrix R. And now my claim is that this still remains a valid commitment to the same vector k. To see that, let us denote the matrix R times A as RA. Then the new commitment can be written as RA, RA times k plus R times mu. If you focus on R times mu, recall that mu was a short vector. The other thing is that R is also sort of short because each entry is just -1 or 1. What this means is that R times mu is also going to be a short vector. And so if you do the opening test with k, it's still going to be true because RA times k is close to the second element. Just to summarize, the re-randomized commitment is still a valid commitment to the same k, so this property holds. Okay, the second property that we wanted from our RRC is unlinkability. Recall that unlinkability means that if we have two commitments and if I re-randomize one of them, you shouldn't be able to tell which one I randomized. And turns out that this commitment scheme is indeed unlinkable based on LWE and leftover hash lemma. But the problem is binding. Recall that to break binding, the adversary needs to find a commitment which is A comma B and two openings k and k prime such that they are both valid. This means that A times k should be close to B and A times k prime should also be close to B. We might hope to get binding based on this claim which says that for a random tall matrix A with high probability there are no k and k prime for which AK is close to AK prime. But the main issue here is that A is not random. Because A is part of the commitment scheme, the adversary can choose a bad matrix A and easily find vectors k and k prime such that AK is close to AK prime. And this is not just a problem in the proof, we can actually attack the SSLE protocol based on this issue. I want to now convince you that this is not an easy problem to solve. We'll try some simple fixes and see that they don't work. So at a high level, what we want to do is that we want to force the adversary to choose a random A matrix so that we can use the claim that we've listed above. One way to do that might be to include the matrix A in public parameters. This way, the adversary has no control over the A matrix and we can assume that it's random. The second option might be to force the adversary to use a random oracle or a hash function to use A. So for example, the commitment could be a seed S, hash of S times K plus mu. Here mu again is the short noise vector as we saw before. But the problem in both these cases is re-randomization breaks down because we now lose the nice structure that we had in our original commitment scheme. Okay, so I'll quickly cover the key observation that we used to solve this issue. So this claims the same as what we saw before. Basically, for random matrix A and random K and K prime, AK is not going to be close to AK prime with a high probability. In other words, for a random vector K and K prime, there are very few matrices A such that AK is close to AK prime. Now, the interesting thing is that you can amplify this. If we choose two random vectors, K1, K2 and K1 prime and K2 prime, then there are even fewer matrices A which map AK1 close to AK1 prime and AK2 close to AK2 prime. In our paper, we show that if you do this n times, meaning if you choose n random vectors K1 to Kn and again K1 prime to Kn prime, then with high probability, there is no matrix A that maps all n pairs of vectors close to each other. The last thing is how would we force the adversary to choose random K vectors? Well, you can just use a hash function. And these ideas are sort of the crux of our main RRC construction, and you can see the details of binding and unlinkability in our paper. Unfortunately, we're still not done. There is one last issue. So recall that we defined unlinkability by saying that if you're given two commitments and I re-randomize one of them, you shouldn't be able to tell which one I randomized. But turns out this is not enough for SSLE. The reason is that these commitments might be re-randomized by a corrupt party. So you can look at a paper for stronger unlinkability definitions which accounts for this issue and also constructions which satisfy this definition. We also have a ring LWE based construction in the paper. And lastly, we also have a lattice based proof of shuffle based on the recent work by Costa Martinez and Morello. Okay, to conclude, SSLE can be useful when you move from proof of work to proof of stake. We constructed a practical SSLE protocol from lattice-based assumptions, which are believed to be post-quantum secure, and we have this new notion that we call re-randomizable commitments. There are still a few open questions. The first one is other applications of RRCs, and secondly, if there are more efficient approaches for SSLE. Thank you.
Thank you. Great stuff. Anyone have any questions? Yeah. We'll go first with Wilson here.
In the shuffle diagram, you stated that one of the parties had to do a zero-knowledge proof that they did the shuffle appropriately. Under what type of zero-knowledge proof are you using, and why is it assumed to be post-quantum secure? Okay,
so there are two cases. So the first construction that we have is based on LWE. So for the proof of shuffle for that, we rely on generic lattice-based zero-knowledge proofs. So like we just cite a few papers and we're assuming that those papers are believed to be post-quantum secure, so we just use them. For the ring LWE case, we actually have an efficient proof of shuffle. So basically, Bear Groth have this minimal shuffle paper from 2012. This paper, Costa Martinez et al., they adapted it to the ring LWE setting. So we use that. So it's a much more efficient lattice-based proof of shuffle, which proves exactly like it's shuffled and randomized correctly, and it's pretty efficient as well. So it's believed to be post-quantum secure.
Great. Yep. We'll go back there. I'll run it back real quick here. I used to play football.
Quick question. Have you estimated concrete parameters and concrete bandwidth of the protocol?
Good question. So we haven't done an implementation yet, but we don't expect to do, so like just at a high level, it's very similar to like general lattice-based commitments. So like it's not going to be as efficient as discrete log, but like it's not much worse compared to lattice-based commitments. So that's all I can say about that. Yeah.
We have time for one more here. Yep.
It was not clear to me, like, after you re-randomize, how do you even know that this is your commitment? Or, like, what is the proof after the re-randomization?
Okay, let me see if I can... Okay. Oops, it's working. Just one sec.
Flash.
Okay, yes, sorry. Okay, so that's in this slide. So basically, if you look at the commitment, it's A comma B, where B is A times K plus mu, right? So once you re-randomize, all we did is that we multiplied both coordinates by a matrix R, right? So now the commitment is RA, comma RAK plus R times mu. So basically, because of the way we sampled mu and because the way we sampled R, the opening test, which is just checking if A times K is close to B, the same opening test still works even if I don't know R. So all I need to know is K, and you can still do the opening test and it works. And we can discuss this offline as well if you want.
Great. Yeah, I think we're right at time. So thank you to Aditi and then everyone else in the first session.